This is your presenter, Asloob Mudassar, and I am presenting slide number 15B of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: LS coupling, atomic nitrogen ground state analysis using LS coupling, symmetry arguments, and wave functions, microstate table. These articles will be covered in the today's lecture. And this is a second lecture of the series categorized as many electron atoms. So in the today's lecture, I shall be covering LS coupling. The interaction energy between Li and Si, that is the orbital angular momentum and spin angular momentum of an electron, is smaller than the interaction energy between two different electrons. For example, smaller than the energy due to LI-SI interaction is smaller than the energy due to LI-LJ interaction and due to SI and SJ interaction of the two electrons labeled as I electron and J electron. And this LISI is for the single electron which is labeled as I electron. So for the ith electron, the interaction energy between the two angular momenta Li and Si is smaller than the interaction energy between their orbital angular momenta Li, Lj and between their spin angular momenta Si and Sj of the two electrons. So it means that when we have the two electrons, then we need to consider Li, Lj interaction to form the total orbital quantity capital L and to have an interaction of Si and Sj to form the total spin angular momentum. So in the LS coupling, I shall be covering the interaction of Li and Lj to form the total angular momentum capital L, and the interaction of Si and Sj will be combined to give you the total spin angular momentum capital S. Individual Li combine vectorially to a total orbital angular momentum capital L. Individual Si combine vectorially to a total spin angular momentum capital S. So here Li mean all orbital angular momenta will combine to give you the total angular momentum L of the atom or the electron, and similarly all the individual spin angular momenta Si will combine vectorially to give you the total spin angular momentum capital S. So when we have created capital L and capital S as the total orbital angular momentum and as the total spin angular momentum, these two quantities will combine. That is L couples with S to form the total angular momentum J of the atom. So far here we have learned that how the J will form. First of all, we shall construct capital L by combining all the Li vectorially, and we shall construct capital S by combining all the Si vectorially, whether I stands for 2 electrons or for 3 electrons or for more electrons. Then capital L and capital S will be combined vectorially to give you the total angular momentum J of the atom. For a 2-electron system like helium, we can write capital L, that is the total orbital angular momentum, is equal to the vectorial sum of the individual angular momentum of the 2 electrons, that is L1 and L2, as given in equation number 3. So capital L will be equal to L1 plus L2 added vectorially. And the magnitude of the total angular momentum L is equal to the square root of L into L plus 1, and outside that one we have H bar. This capital L inside the square root is actually the orbital quantum number, and the quantity which with a vector with an arrowhead over it, that is capital L with a vector sign, is actually the angular momentum vector. And without the vectorial notation, this is actually the orbital quantum number. So on the right hand side in the square root sign, I have the total orbital quantum number, whereas on the left hand side I have the magnitude of the orbital angular momentum as shown in equation number 4. Now we can write that capital L is equal to mod of L1 plus L2, and this includes all intermediate values. For example, we shall add L1 plus L2, we shall subtract L1 plus L2, and we shall write all the intermediate values between L1 plus L2 and L1 minus L2, which is shown in the line over here. That is capital L is equal to L1 plus L2, comma, L1 plus L2 minus 1, comma, L1 plus L2 minus 2, and so on. And the last term will be L1 minus L2. Here I have assumed that L1 is greater than L2. The total quantum number L determines the term symbols. For example, when you have capital L is equal to 0, 1, 2, 3, and so on, then the term symbol corresponding to the corresponding to the value of capital L will be equal to capital S, corresponding to L is equal to 0. Capital P is the term notation corresponding to capital L is equal to 1. Capital D is the term notation corresponding to capital L equal to 2. Capital F is the term notation corresponding to capital L is equal to 3, and so on. Note that capital L is equal to 1 does not mean that one of the individual electrons is in the p state. So when we have formed the total quantum number or total orbital quantum number L, then it does not describe the state of the individual atoms, but it collectively describes the state of two or more electrons, whatever the case may be. Coupling of orbital angular momenta of two electrons L1 and L2 to form the total angular momentum capital L is demonstrated graphically. For example, for the D term, we have L1. I have assumed that all L1 and L2 have a magnitude equal to 1. That is, the orbital quantum number of the individual electrons has a magnitude equal to 1. So here L1 is equal to 1, L2 is equal to 1. So when they combine together in the linear fashion, that is, both have the same direction, then of course the total value of capital L vector will be equal to 2. So this will correspond to the D term. Now let's come to the P term. In the P term, L1 is equal to 1 and L2 is equal to 1. They have the same magnitude, but they have different orientations, and they are combined in such a way that the resultant vector, that is the resultant orbital angular momentum capital L is equal to 1. So since capital L is equal to 1, this will form the P term. Now in the third diagram, you can see that L2 and L1 both have the same magnitude but opposite directions, and their resultant will be equal to 0. That is, capital L will be equal to 0. So this capital L is equal to 0 will correspond to the S term. So you see that I have explained the S term, the P term, and the D term graphically, that how the individual orbital angular momenta are combined to give you the total angular momenta capital L, having a value capital L is equal to 0 for the S term, capital L is equal to 1 for the P term, and capital L is equal to 2 for the D terms. Selection rule for the optical transitions. So you see that if you have many states, then of course there is a possibility of transition between them. And that is given by, that is, if we have the case of a single electron, then for the single electron, the selection rule is delta L is change delta L, that is the change in orbital quantum number L is equal to plus minus 1. And if you have two or more electrons, then you have delta capital L is equal to 0 plus minus 1. That is the change in the total orbital quantum number of the system will be equal to 0 and plus minus 1 for the optical transitions. Delta L is equal to 0 means that the quantum states of two electrons change simultaneously and in opposite directions. So when we have delta L is equal to 0, it means that the quantum states of the two electrons change simultaneously and in opposite directions. This happens when the coupling is strong, which is the case in heavy atoms. So for the case of heavy atoms, delta L is equal to 0 will be applicable to heavy atoms in which the quantum states of the two electrons change simultaneously and in opposite directions to give you the possibility of allowed value delta L is equal to 0. And this is applicable only for heavy atoms. Now for the total spin capital S, that is the total spin angular momentum capital S is equal to the vectorial sum of the individual spin angular momenta S1 and S2 as shown in equation number 6. And in magnitude form, the magnitude of the spin angular momentum capital S on the left hand side is equal to the square root of capital S into capital S plus 1, and outside that one we have h bar, and the capital S in the square root is actually the total spin quantum number. So on the right hand side, capital S stands for the total spin quantum number, and on the left hand side, the mod of capital S vector. Capital S vector is actually the magnitude of the spin angular momentum. So the quantity on the left is actually the magnitude of angular momentum, spin angular momentum, magnitude of the total spin angular momentum, whereas on the right hand side, capital S stands for the total spin quantum number. And the total spin quantum number can also be given as capital S is equal to mod of S1 plus minus S2. So here only two values are allowed. Capital S could be sum of these two quantum numbers, S1 plus S2 or S1 minus S2. And you know that the value of S1 and S2 both have a value equal to half. And here I am assuming that S1 is greater than or equal to S2. And this condition that S1 is greater than equal to S2 will be applicable for a system having more than two electrons. But if there are only two electrons, it doesn't mean that which one is greater or which one is smaller, because both will have the same value equal to half. Since S1 for the two electron system, since S1 is equal to half, S2 is equal to half, the capital S could equal the total spin quantum number could either capital will be equal to S is equal to 1 or S is equal to 0. Capital S is equal to 0. For optical dipole radiation, the selection rule is delta S is equal to 0. That is, the change in spin is equal to 0. This is the allowed dipole moment. That is, the transition will takes place between the two states having the same value of the total spin quantum number. That is, either it is S is equal to capital 1 or S is equal to capital S is equal to 0. So the transition from capital S is equal to 1 to capital S is equal to 1 will take place. Or the transition from capital S is equal to 0 to capital S is equal to 0 will take place, because for both these such transitions, delta S is equal to 0. That is, the spin flipping is not associated with optical dipole transitions. That is the transition from capital S is equal to 1 to capital S is equal to 0, where the spin flips is not allowed in the optical dipole radiation. The interaction between the spin angular momentum, or more accurately, the spin magnetic moment, and the BL. You know that BL is actually arises from the total angular momentum L of the atom. So that's why I have a subscript capital L over here with B. So B is the internal magnetic field which arises because of the orbital angular momentum L of the system. So you see that in the atom, mu s, which is the spin magnetic moment, will interact with BL, and results in a coupling of capital L and capital S, which we actually the coupling is in between mu S and BL, which we interpret as the coupling between orbital angular momentum L and the spin angular momentum S to form the total angular momentum J of the atom. So in principle, the coupling will be between the spin magnetic momentum US and the orbital magnetic field BL. So these two will interact, which means that capital L and capital S will interact to form the total angular momentum J of the atom. So this J, which is the total angular momentum written in the vectorial form, all the quantities written in the vectorial form are actually the angular momenta. So the angular momentum, total angular momentum J of the atom is equal to the vectorial sum of the orbital angular momentum and the spin angular momentum, and its magnitude form is given in equation number 10, which is the magnitude of the total angular momentum J of the atom is equal to the square root of J into J plus 1, and outside that one we have H bar, where J inside the square root sign is actually the quantum number, total quantum number, whereas whereas the mod of J vector is actually the mod of the total angular momentum of the atom, whereas J inside the square root is actually the total quantum number. So on the right hand side we have the quantum number, on the left hand side we have a quantity which is the angular momentum, total angular momentum of the atom, and its magnitude and its value, that is the value of the total quantum number J, is given by total quantum number J can be found from the expression that is the mod of L plus minus S, where L and S are the quantum numbers and J is also the quantum numbers as shown in equation number 11. So all the terms which I write without a vectorial notation, they are actually the quantum numbers. So J will have the possible values. J is equal to L plus S, then L plus S minus 1, then L plus S minus 2, and so on. And the last term will be L minus S. Here I am assuming that L is greater than S. For several electron systems, there are two S plus 1 possible orientations of capital S with respect to capital L. So you see that 2s plus 1, which is also called the multiplicity of the system, will give you the possible orientations of the spin angular momentum with respect to the orbital angular momentum. That is, the multiplicity of the term is 2s plus 1 if L is greater than S. Possible couplings when capital S is equal to 1 and capital L is equal to 2 is shown in the figure below. So you see that here I am assuming that capital S is equal to 1. That is, the total spin quantum number is 1 and the orbital quantum number L is equal to 2. Now I am adding them in the vectorial form. So you see that here you have capital S vector, that is the spin angular momentum, has a magnitude equal to 1, and the orbital angular momentum has a magnitude equal to 2, shown in the red. So these two vectors will combine together. Here I am showing that both are in the same direction. The total J will be equal to simply the addition of their magnitudes. So capital J will be equal to 3 and will have the same direction as that of the direction of capital S or the direction of capital L. Now in the middle figure, I have S is equal to capital 1 and L is equal to capital 2, but they are making some angle between them in such a way that when you add L is equal to 2 vector to S is equal to 1 vector, you get the total value equal to 2. So this is J in the vectorial form, that is the total angular momentum of the atom J is equal to 2 in the figure, in the middle figure. Now in the rightmost figure, I have capital L is equal to 2 and capital S is equal to 1, but the spin angular momentum is oriented opposite in the direction to the orbital angular momentum. So the total angular momentum J of the vector J of the atom has a total magnitude equal to 1 and its direction is along the direction of the vector L. So formation of J is equal to 1, 2, 3, when S is equal to 1 and L is equal to 2 are shown graphically in the figure. So you see that I have shown in this figure that you can construct total angular momentum of the atom J is equal to 1, J is equal to 2, and J is equal to 3 by adding by acting two quantities, that is the spin angular momentum and the orbital angular momentum, having a magnitude respectively equal to 1 and equal to 2 over here, and I have shown their addition over here. In the spectra of the helium, there are two systems, singlet system and the triplet system, which I have explained in the previous lecture. And the transitions between these two systems, that is the cross transition, is forbidden, and we say that delta S is equal to 0. That is, the spin flipping is not allowed. So only the transition with the delta S is equal to 0. That is, the terms in the singlet terms can make the transitions. So the transition is possible between the singlet terms, for which delta S will be equal to 0, and also the transition for the triplet terms are allowed within the triplet system, that is the delta S is equal to 0 in both of these systems. But from the transition from the singlet to triplet and from the triplet to singlet will not be equal to 0, because for such a system delta S will be equal to 1. Complete nomenclature of terms or energy states of an atom can be written as N. This N is the principal quantum number. This capital L stands for these term symbols. Capital S, it could be capital S, capital P, capital D, capital F, etc., depending upon the value of capital L, which is the orbital quantum number. So if orbital quantum number is 0, we have the term symbol S, capital S. If orbital quantum number L is equal to 1, we have the term symbol capital P. If orbital quantum number has a value equal to 2, we have the term symbol D. And similarly, if the orbital quantum number has a value equal to 3, we have the term symbol equal to F. And this M, which is a superscript before the letter S, is actually the multiplicity of the term. And multiplicity has a value, a formula which is given by capital M is equal to 2S plus 1. And you know that I have described that in the multiplicity will give you the number of possible orientations of the spin angular momentum with respect to the orbital angular momentum of the atom. So this is what the physical meaning of the multiplicity. And here I have capital J. Capital J is actually the total angular momentum quantum number of the atom. So you see that all the spectroscopic terms will be written like this. You need to specify principal quantum number, you need to specify the total quantum number, you need to have the value of the orbital quantum number, and then of course you need to have the value of the spin quantum number, so that you can calculate the multiplicity capital M. Now we are going to talk about, since we are talking about many electron systems, the possible multiplicities are shown below. That is, for two electron system, there are two possible values of capital S. Either capital S is equal to 0 or capital S is equal to 1. When capital S is equal to 0, we have the single term, because multiplicity will be equal to capital 1. And when S is equal to 1, the multiplicity will be equal to 3. So this is referred to as the triplet system. That is, to each term, there will be 3 terms. So for 3 electrons, capital S is equal to half, and capital S is equal to 3 by T. Only for 3 electrons, we have 2 possible values. Either capital S will be equal to 1 or capital S is equal to 3 by 2. And when capital S is equal to half, the multiplicity is 2. That is why the system is called a doublet system. When S is equal to 3 by 2, then of course the multiplicity will be 4. And this system is called quartet system. So for the 3 electron, we have the doublet system and the quartet system. For 4 electrons, 3 possible values of the spin quantum number are allowed. That is, capital S is either equal to 0, capital S is equal to 1 or capital S is equal to 0 or 2. When capital S is equal to 0, the multiplicity will be equal to 1. The system is called a singular system. When capital S is equal to 1, the multiplicity is equal to 3. That is, the system is a triplet. When S is equal to C, when S is equal to 2, the multiplicity is equal to 5. The system is called a quintet system. For 5 electrons, there are 3 possible values of capital S. That is 3 possible values of the spin quantum number. Capital S is equal to half, capital S is equal to 3 by 2, capital S is equal to 5 by 2. So when capital S is equal to half, you have a multiplicity equal to 2. The system is called doublet. When capital S is equal to 3 by 2, the system has a multiplicity equal to 4. The system is called quartet. When capital S is equal to 5 by 2, the system has a multiplicity is equal to 6. The system is called sextet. So you see there are up to 5 electrons. I have given you the descriptions and the term symbols and also the name of the terms along with the value of the spin quantum numbers. And the names of these terms are after the name of multiplicity. That is, what is the value of a multiplicity? According to that one, we name the terms. For example, if the multiplicity is equal to 0, if the multiplicity is equal to 1, the term is called a singlet. If the multiplicity is equal to 2, the term is called doublet, and so on and so forth. Analysis of energy terms of the nitrogen atom. Now you see that here I am going to study the atomic nitrogen, not in molecular form, but in atomic form. In the atomic form, the nitrogen atom has a total 7 of electrons, and 4 of the electrons are in the closed shells of 1s2 and 2s2, and the rest of the 3 electrons are in the 3p orbitals, where there is a lot of space. That is, the 3 electrons in the 2p3 configuration can occupy electrons in parallel spin. That is, there are 3 2p electrons outside the closed s orbitals. The energy terms will be doublet and quartet, as we have explained for the case of 3 electron. All the 3 electrons begin in the same subshell are equivalent. So since all the 3 electrons are in the same subshell, that is in the p subshell, we cannot discriminate between those electrons. So such electrons will be regarded as identical fermions or identical electrons. For that one, we have L1 is equal to 1. L1 is equal to 1. That is, the orbital angular momentum of the first electron is 1. Similarly, the orbital angular momentum of the second electron is 2. The orbital angular momentum of the third electron is 1. So L1 is equal to 1, L2 is equal to 1, L3 is equal to 1. And the corresponding spins are S1 is equal to half for the first electron, S2 is equal to half for the second electron, S3 is equal to half for the third electron. In principle, there is no discrimination for the electrons. So the labels S1, S2, and S3 are arbitrary. Now you see that first of all, I am going to give you the description when the 2 electrons are combined to give you the total angular momentum L of the atom and the total spin of the atom equal to S when only the 2 electrons will combine. So for example, capital S is equal to mod of L1 plus L2, which is mod of 1 plus 1. So that is equal to 210, because you add 1 plus 1 to you get 2, you subtract 1 minus 1, you get 0, and there all the values between them are also written. So 210 are actually the possible values when the 2 electrons combine. So when you combine these values with the third angular momentum, here it should be L plus minus L3, not L2. So you are putting the value within the parentheses as 210 coupled with plus minus 1. Then you have 4 values 3, 2, 1, 0, and so since capital L has a value equal to 3, 2, 1, 0, so the term symbols will be equal to capital F, capital D, capital P, and capital S respectively. So now let's talk about S1, S2, and S3. So according to, so you see that since the 3 electrons are there and there is a total vacancy of 6 electrons in the p orbitals, so all these electrons will have their spins parallel. So S1 mod of S1 plus S2 is equal to half plus half is equal to 1. I have ignored the negative sign because the spins are parallel. So I need to just add them. So in the next second step, I am going to add 1 plus minus S3. So here you see that correspondingly it should be L3 over here. So mistakenly I have used L2 again. So here I have correction, that is capital S is equal to 1, which is this value plus minus S3. So the mod of 1 plus half. Again you see that I am using the positive sign because all the 3 electrons have the same spin. So 1 plus half will equal to 3 by 2. And if you put 3 by 2 over here, you will get multiplicity equal to 4. So this is what you see that I have given how the orbital, how the 3 orbital quantum numbers can be combined and how the 3 spin quantum numbers can be combined to give you the total spin capital S, and similarly to give you the total value of the orbital quantum number capital L. Now you see that I am going to give you some symmetry arguments. Actually, symmetry arguments will help you to see that which of the states are allowed and which of the states are not allowed. Actually, symmetry arguments is a method that allow you to check which of the state will be possible and which of the states will not be possible. In 2p3, the 3 fermions, that is the 3 electrons each of state 2p, are identical, and Pauli exclusion principle would determine which capital L and capital S combinations are allowed. So you see that here we shall base our selection on the Pauli exclusion principle to determine which of the L and S combinations are allowed. But here we shall refer to them as the symmetry argument analysis. For identical fermions, the total wave function. So you see that this point is very important, which I am going to make. That is for identical fermions, which is the case in this, which is the present case. That is 3 fermions are identical. So for identical fermions, the total wave function must be antisymmetric. That is, the wave function must change sign if any 2 electrons are swapped. So if you construct a wave function for the two, for example, for 2 electron system or for 3 electron system, if you swap any 2 electrons, the wave functions must change its sign. Such a system is called antisymmetric system. So you see that for our 3 fermions, since identical, the symmetry arguments require that our wave function should be antisymmetric. Now let's see our wave functions. So you see that here I can represent my total wave function psi total, written on the left hand side, is equal to psi space, which is a function of total, or which is a function of orbital angular momentum multiplied by psi spin, and psi spin is a function of the spin angular momentum. This equation is shown in 12. So you see that in equation number 12, we have the two wave functions being multiplied on the right hand side, giving the total wave function psi total. So you see that if psi total is antisymmetric for a given value of capital L and for a given value of capital S, then of course the total wave function, if antisymmetric, then those states for the value of L and for the value of S will be allowed. Otherwise, the term state will not be allowed. So psi total has to be antisymmetric. So, so if psi space is antisymmetric, then psi spin must be symmetric and vice versa. Thus, that is, if psi space is symmetric, psi spin must be antisymmetric and vice versa to ensure that psi total stays antisymmetric. For 2p3, symmetries become even more complex than just being even or odd. So you see that here I am discussing only two types of symmetries, that is symmetric and antisymmetric. But you know that the symmetries can even be more complex in some situations. That is, we have a mixed symmetric case. So for 2p3, the symmetries become even more complex than just being even or odd, or being symmetric or antisymmetric. Such complex symmetries involve group theory and Young tableau. When capital S is equal to 3 half, that is, all spins are aligned parallel, is a total symmetric case. So you see that in our 3 electron system, that is the system that we are discussing presently, that is the atomic nitrogen. If all the 3 electrons in the 2p3 orbital have parallel spins, which they do, then of course the system is referred to as the total symmetric case. That is, the spin will be total symmetric and the value of the spin will be equal to 3 half, because all the spins will add together. Half plus half will give you capital S is equal to 3 half. That is, they all have the same orientations. That is, the case is of a total symmetric case with respect to the spin. Now you see that let's make a selection that to choose L is equal to 0. That is, either L is equal to 0 is allowed or not allowed for over 3 electron system. So you see that I have discussed over 3 electron. I am discussing over 3 electron system. And you know that when we are discussing over 3 electron system, we know that the total values of capital L will be equal to 0, 1, 2, 3, and so on. And so here I am going to check the value of either capital L is equal to 0 is allowed or not using the symmetry arguments. To choose that whether capital L is equal to 0 is allowed or not allowed, is an allowed state or is an unallowed state, the associated wave function must be antisymmetric. That is, using capital L is equal to 0 and capital S is equal to 3 by 2 in their corresponding wave functions. If their wave functions are combined together and the total wave function is antisymmetric, then we shall say that the state L is equal to 0 is an allowed state. Let's see. For the 3 electrons to be in the p orbital, the first state could be L is equal to 1, ML is equal to 0, and plus minus 1. That is, I can write 3 possible combinations or 3 sets. L is equal to 1, ML is equal to 0, L is equal to 1, ML is equal to plus 1, L is equal to 1, ML is equal to minus 1. The resultant wave function is antisymmetric. You see that the values which I have written, that is ML is equal to 0, ML is equal to plus 1, ML is equal to minus 1. These are different values, and these 3 values of ML which are equal to 0 plus minus 1, they are not symmetric. So we shall say that L is equal to 0 state is thus allowed, because the wave functions due to L is equal to 0 is an anti-symmetric function, whereas the wave function due to S is equal to 3 half is a symmetric function. That is, the spin wave function is a symmetric wave function for the value of S is equal to 3 half, whereas the space wave function for which depends upon the orbital quantum number, and if the orbital quantum number is equal to 0, then we have seen through these combinations of the orbital quantum numbers that the orbital quantum numbers will be antisymmetric, so the wave functions will also be antisymmetric. So L is equal to state L is equal to 0, which is the S state, is an antisymmetric function. The two wave functions will multiply together to give you a resultant antisymmetric function. On that basis, we shall say that capital L is a state, that is S state is thus an allowed state. And since we have capital S is equal to 3 by 2, the corresponding multiplicity which is given by 2s plus 1, and this value will be equal to 4, so the multiplicity will be 4. So we can write the multiplicity with this allowed state, thus 4s is an allowed state. So you see that using the value of capital L is equal to 0, putting over here, we found that this psi space is an antisymmetric function, and putting the value of capital S is equal to 3 by 2, in which all the spins are parallel to each other, we found that Y spin is a symmetric function. So Y spin is symmetric, Y space is antisymmetric. The product of these two one makes the Y total also antisymmetric. It means that Y is equal to 0 is an allowed state. So L is equal to 0, which is an S state, is an allowed state, and I have written the multiplicity with that one. So 4S is an allowed state. Let us check the status of 2s state. You know that I have discussed L is equal to 0 state over here using the symmetry arguments. And I have found that the state corresponding to L is equal to 0 with the multiplicity equal to 4 is an allowed state. So let's check that if L is equal to 0 with the multiplicity with capital S not equal to 3 by 2 but has different values. For example, let's suppose different values not equal to 3 by 2 but different values. Under that condition, what will happen to the allowed value of S? Because when L is equal to 0, S is allowed. We have confirmed that one on the basis that S is equal to 3 half. But now if S is not equal to 3 half, what will happen? Let us check the status of 2s state, which belongs to capital L is equal to 0, which has anti-symmetric wave function y psi, y space of L, and the multiplicity. We have already determined that capital L is equal to 0 makes the wave function, makes the y space function to be anti-symmetric. This is what we have established in the previous paragraph. Now, this 2 means that the multiplicity is 2, and this 2 means that the multiplicity is 2, that is capital S has a value equal to half, which belongs to this case, because plus half will cancel with the minus half, and only the last one will contribute as the spin, which has a value of half. So each of these spin has a value equal to half. So the first one has a value of a plus half, the other one which is downward has a value of a minus half, the third one again has a value of a plus half, and two of them will cancel out, and the resultant value of the spin quantum number will be equal to plus half. And the corresponding wave function psi spin of S is actually anti-symmetric because of the spin pattern which is anti-symmetric. So both cannot be antisymmetric. So you see that we have already established in the previous paragraph that y space of L for the value of L is equal to 0 is an antisymmetric function. But here we have established that y spin for a value of spin capital S is equal to half is an antisymmetric function. So both are antisymmetric function. Their product will not be antisymmetric in that sense. So both cannot be antisymmetric. Thus, the 2s state is not an allowed state. So you see that out of these allowed values, we have checked the lowest value of L equal to 0. And we have seen and we have checked the value of L is equal to 0 for two multiplicities. Either multiplicity is equal to 4 and multiplicity is equal to 2. That is, we are going to check the state 4s and 2s. We have found that the 4s state is an allowed state, and we have also found that the 2s state, that is the state with the multiplicity 2, is not an allowed state. Similarly, we can also check the P state, D state, and F state on similar grounds, that is on symmetry arguments. So now let's check the P states. That is these two states, P state and D state with multiplicity equal to 2. Let us check the status of 2p and 2d states, which belong to capital L is equal to 1 and capital L is equal to 2 respectively, and have mixed symmetries. So we have already declared that these 2p and 2d states have mixed symmetries. That is, they are neither symmetric nor antisymmetric, but have mixed symmetries. The spin capital S is equal to half, which has antisymmetric wave function. The multiplicity m is equal to 2, giving you capital S is equal to half, has opposite spins. That is either this combination, parallel, anti-parallel, parallel, or both parallel, anti-parallel, or anti-parallel and both parallel, etc. which is a state of mixed symmetry also. That is neither totally symmetric nor totally antisymmetric. The overall wave function due to spin, that is the spin wave function, is an antisymmetric wave function. And we have also seen that these 2p and 2d states with values capital L is equal to 1 and 2 will have mixed symmetries. Thus, the states 2p and 2d are allowed states. Because the states L is equal to 1 and 2 are actually mixed symmetries and more inclined towards the symmetric things, whereas the spin wave function is totally antisymmetric, and due to that one we would say that 2p and 2d are the allowed states, because the total and the resultant wave function psi total will be antisymmetric in this case. You can also check yourself that why P state and D state have mixed symmetries in the same fashion. I have checked the L is equal to 0 state. With while writing its total, while writing its states of quantum numbers, which will also be explained later. Now let's check the 4p and 4d states. Before that, I checked the 2p and 2d states. That is the that is p 2p doublet and the 2d doublet states have been checked and found these are allowed states. Now let's check the 4p and 4d states. So let us check the states of 4p and 4d states which belong to L is equal to 2 and 3 respectively, and their corresponding wave functions are not perfectly antisymmetric. So actually I am making a mistake. For P, I have value of capital L is equal to 1, and for D, the value of capital L is equal to 2, which I have mistakenly written as a 2 and 3. It should be actually 1 and 2, as described in this case. For the P and D state, I have capital L is equal to 1 and 2. Similarly, for this case, capital L should be equal to 1 and 2. So this is mistakenly written as 2 and 3. And their corresponding wave functions are not perfectly antisymmetric and have mixed symmetries. Multiplicity M is equal to 4 means that capital S is equal to 3 by 2. That is, all have the same, all the 3 electrons or the fermions have the same symmetry, have the same orientations. That is the wave function due to spin is a symmetric, is a totally symmetric wave function, because S is equal to 3 by 2 gives you totally symmetric wave function. Whereas for the case of 4p and 4d, we have seen that this is the case of mixed symmetries. So Y wave function Y space is a has a mixed symmetry, whereas the Y spin has is a totally symmetric wave function. The overall wave function is not antisymmetric. Thus, the states 4p and 4d are not allowed states. So, through the symmetry arguments, we have found that 4s, 2p, and 2d can exist for the ground state 2p3 of the nitrogen. So you see that here on the basis of this one, we can confirm that which states are allowed and which states are not allowed. This approach is called the symmetry approach. That is the symmetry argument approach is used, because I am not going to mention to give you these wave functions, because these wave functions are encountered in the study of these concepts through in quantum mechanical description. So the wave functions, when known, you can plug in the values of these values by yourself, and you can explicitly determine whether these functions are symmetric or not, and what is the behavior of the total wave function. So if total psi total is antisymmetric, then of course the state with the value of capital L and with the value of capital S are the allowed state. Otherwise, they will not be, the states will not be allowed if psi total is not antisymmetric. So for the ground states of the nitrogen, we have found 4s, 2p and 2d are the allowed states for the ground states of the nitrogen. Now you see that there is another approach which we call an alternative approach, alternative to the previous symmetry arguments approach, or and this approach is referred to as the microstate table approach. And here I shall demonstrate how microstate table approach can be used to determine which of the states are allowed and which of the states are not allowed. So this is more powerful than the symmetry arguments approach. For this table, we must list down all combinations of ML, that is all, and MS, that is all combinations of the orbital magnetic quantum number and this magnetic spin quantum number. So all combinations of these two magnetic quantum number will be written that do not violate Pauli exclusion principle. For the first 2p orbital, the value is L is equal to 1, ML is equal to 0 plus minus 1, MS is equal to plus minus half. That is, for each value of ML, the value of MS will either be spin up or spin down. That is, two values of MS are allowed. Similarly, for the second p electron, L is equal to 1, ML is equal to 0 plus minus 1, and MS is equal to again 0 plus minus 1. For the third electron, for the third 2p electron, again L is equal to 1, ML is equal to 0 plus minus 1, MS is equal to plus minus half. Here you may label them ML1, ML2, ML3, and correspondingly MS1, MS2, MS3. For each set or row, we shall list down all possible values of ML and MS subject to the Pauli principle, according to which no two rows in a single microstate, that is, in a single set of electrons, can be identical. That is, the quantum numbers of the states should be different. The quantum states of all these three electrons should not be identical. That is, no two electrons should have the same quantum numbers. This is not allowed by the Pauli principle. The set 1 up, 0 up, minus 1 up is the same as 0 up, minus 1 up, 1 up. We shall count only unique sets, and they are 20 in numbers. So you see that I am going to discuss these sets in much greater detail in the next pages, and there it will be clear what is the meaning of these sets that I have written. So you see that for each of these electrons, I have three values of ML and two values of MS. So you see that these are the total 3 multiplied by 2 are the 6 values. So if you can arrange these 6 values into 3 unique numbers, then of course the total number of numbers will be equal to 2. So the 20 unique numbers can be constructed using these 6 numbers. So 6. So you see that in the binomial theorem you encounter NCR, the coefficients which determine the probability of the states. Similarly, I have NCR, here n is equal to 3 and r is here n is equal to 6 and r is equal to 3. And if you expand this NCR, that is the factorial of 6 divided by the factorial of 3 divided by the factorial of 6 minus 3, you will get the number equal to 20. So it means that the 20 unique sets will be possible. So let's discuss these 20 possible sets. So I am going to discuss the microstate table for the three 2p electrons of the ground states of the nitrogen atom. So you see that I shall construct this product ML1 with MS1, ML2 with MS2, ML3 with MS3. So I shall construct this product. For all possible products will be constructed, and the product will have ML1 and MS1, product of these two quantities. So this quantity, which is MS1, can either have spin up and spin down. So if you have plus half, it will be spin up. If you have a minus half, it will be spin down, and so on. So you see that I have possible values of MS. You see that this capital MS is actually the resultant of these small ms values, and each small ms has a value equal to half. So ms1 is equal to half, ms2 is equal to half, ms3 is equal to half. So you can combine them in different ways to construct the total ms equal to plus 3 by 2, plus half minus 3 by 2. These are the possible values of the combination of these three ms1, ms2, ms3 values, and each of them is equal to plus half or minus half. Now I am writing the total ml allowed values. You know that when the value of capital L is equal to 2, the allowed values will be equal to plus 2, plus 1, 0, minus 1, and minus 2. So I have written these values of capital L. Capital L is equal to 0, plus minus 1, and plus minus 2. These are the allowed values of capital M. And of course, the allowed values of a capital M can be constructed by combining ML values. So ML1, ML2, ML3, these values can be combined to give you the total value ML. Later, I shall show you that this capital M, capital MS is equal to, is actually the summation of all MS values, and capital ML is actually the summation of all ML values. So for example, let me demonstrate capital MS is equal to summation of MS. So if S is equal to half, S2 is equal to half, S3 is equal to half for the 3 electrons, then the possible values of the spin magnetic quantum number will be plus minus half, plus minus half, plus minus half for each of these spin quantum numbers. So if you set plus ms is equal to plus 3 by 2, then you need to add them as plus half, plus half, plus half. If you want to create plus half, then you have three values. Both should have plus half, and the third one should have minus half. The order is not important. And similarly, if you want to construct a minus 3 by 2, all should have values equal to minus half, minus half, minus half. Order of placing these half values is not important. And if you want to construct a minus half, you can sum up the three values minus half, and plus half. The order of these arrangements is not important. So combining all these one, you will get the values equal to minus half. Similarly, if you want to construct a capital ML, you can construct them using the value of combining all the ML values. And you know that the ML values are ML1 is equal to 0 plus minus 1, ML2 is equal to also 0 plus minus 1, ML3 is also 0 plus minus 1, because for each of the electron, since the electron is a p electron, and for the p electron we have the value of L1, L2, L3, each value equal to 1, and so for each value L equal to 1, we have the magnetic orbital magnetic number equal to 0 plus minus 1, 0 plus minus 1, 0 plus minus 1. That's why I have written them as ML1, ML2, ML3. So the total ML that we want to construct out of these is plus 2, plus 1, 0, minus 1, minus 2. So if you have a plus 2, you have a summation of a plus 1, and 0. The order of these plus 1, and 0 is not important. Similarly, if you want to construct a minus 2, you can combine them minus 1, comma 0. Similarly, if you want to construct a plus 1, there are two possibilities that the plus 1 is constructed. Either you have plus 1, plus 1, minus 1 in any order, or you have plus 1 and comma 0, comma 0. Similarly, you can construct minus 1 in two different ways. Summation of a minus 1 plus 1 in any order, and then you can also construct minus 1 using the combination minus 1 comma 0 comma 0. And of course, if you want to construct 0, the possibility is that you can have plus 1 comma 0 comma minus 1, because all the 0 is not allowed over here. So you see that I have given you the description how you can construct a capital M and how you can construct a capital S values, MS values. And you know that you can combine these values over there. That is the MS1 and ML1 values can be combined over here. ML1, MS1, comma ML2, MS2, comma ML3, MS3. So you can combine these values, noticing the values that must match over here, and the values of ms should be 3 by 2, half minus 3 by 2. The values of ml is equal to plus 2 plus 1, 0 is similarly minus 1 and minus 2. So let's talk about ml is equal to plus 2. So if you want to have ml is equal to plus 2, you can have this one plus 2 only when ms is equal to plus half and ms is equal to minus half. Only these two values, that is ms is equal to plus half and ms is equal to minus half, will allow you to construct ml with the value plus 2, and the combination is shown over here. So plus 1 up, plus 1 down, and 0 up. So if you add the coefficients of these arrows, you will see you have ml is equal to 2. And if you add the notation, if you add the values corresponding to these arrows, you will see it is equal to plus half. Similarly, to construct minus half, to construct ml is equal to plus 2 using ms is equal to minus half, you can have this set plus 1 up, plus 1 down, 0 down. And you see that here you have two quantities plus 1 and the third quantity is equal to 0. So you can notice the arrows. The two arrows are in the downward direction, which is equal to minus half, and one arrow is plus half. So this plus half arrow will be cancelled with the down arrow with minus half, and the resultant will be minus half. So minus half is there. And if you add the coefficients of these arrows, that is plus 1 and plus 2, you get a plus 2 over here. Plus 1 will give you plus 2. So you see that similarly, you can construct all these possible allowed values of the microstate table. For example, for the plus 1, you have 4 sets. For the value of 0, how many sets are there? 2 sets correspond to, one set corresponds to plus 3 by 2, one set corresponds to minus 3 by 2, the rest of the sets correspond to plus half and minus half. And these are 8 values. So corresponding to 0, you have 8 values. Corresponding to 1 plus 1, you have 4 values. Corresponding to plus 2, you have 2 values. Similarly, corresponding to minus 1, ml is equal to minus 1, you have 4 sets. Similarly, corresponding to minus 2, you have 2 sets over here. So the total number of these sets are actually 20. You can count them by yourself. So the 20 values are allowed. And this is what I have explained. Now you see that I am going to explain how we shall use this microstate table discussed a minute ago. How we can use that table in order to check whether a state is known or not, or is allowed or not allowed. The term designation will be equal to 2s plus 1, that is the multiplicity, is written as a superscript before the symbol, and L stands for the symbol, capital L. So look for the highest value of ML. Now the rule is that if you want to construct a state, look for the highest value of ML and MS. And you know that in the table, the highest value of ML is equal to 2 and the highest value of MS is equal to plus 2. ms is equal to half corresponding to ml is equal to 2. So if you corresponding to ml is equal to plus 2, the highest value is plus half. Plus half. So capital ML is equal to 2, capital MS is equal to half. These are the allowed values because we have selected the value of MS is equal to 2 on the basis that it is the highest value. And among the other values for which ML is equal to 2 is allowed, there were two values plus half and minus half, and I have selected the maximum value which is MS is equal to plus half. And you know that when ml is equal to 2, it means that ml goes up to 0, plus minus 1, plus minus 2, and so on up to plus minus l. So it means the value of capital L is equal to 2, because capital L is equal to the maximum value of ml. So capital L is equal to 2. This is paired with the, because when ms is equal to half, the allowed value of capital S is equal to half. And that is the multiplicity is equal to 2. And when L is equal to 2, it means that we have the D state. That is, the term symbol is D. So the resultant state is 2D. So 2D is the allowed state. 2D is the allowed state. D is due to L is equal to 2. And this 2, which is the multiplicity, is due to capital S is equal to half, which is derived from S is equal to half. So you see that the allowed state is 2D. Now the number of microstates counted. How many times this 2D state occurs? It occurs by the time by the number that is equal to 2L plus 1 times 2S plus 1. So put the value of capital L is equal to 2, put the value of capital S is equal to half, then multiply, then together you will get 10. So it means that the state 2D will occur 10 times for the ground state. It might be a degenerate state or maybe non-degenerate state. We are not going to discuss that at the moment. But its total number of microstates containing 2D states will be equal to 10 in the number. Now we subtract one microstate from each of the two boxes. So you see that initially our ML values were 2, 1, 0, minus 1, minus 2, and MS values were plus minus 3 by 2, plus minus half. So you see that I am going to subtract the highest values of these. So I am going to eliminate 2 from this set, and of course minus 2 will also be eliminated. The rest of the values is 1, 0, minus 1, and here I am going to subtract plus minus 3 by 2, and the rest of the value is plus minus half. So we are going to subtract the maximum values because we have dealt them before. Now we have ML containing 3 values, MS containing plus minus half. Now from the value of this, that is 1, 0, minus 1, the maximum value of ML is equal to 1, and from this table the maximum value of MS is equal to plus half. So it means that when ML is equal to plus 1, then of course the value of ML will be equal to plus L. So it will ML is equal to plus 1, and this will be compared with S is equal to half, because half is derived from MS is equal to half. So capital L is equal to 1 will be paired with capital S is equal to half. The resultant state will be 2P, because the P symbol corresponds to L is equal to 1 and S to S is equal to half. We have the multiplicity is equal to 2. So this is the doublet case. So 2P is an allowed state. Now the number of microstates counted is equal to 2L plus 1 times 2S plus 1. So putting the value of L is equal to 1 and S is equal to half, you will get that this state, which is the 2P state, can occur 6 times in the spectrum. Now you see that if you now reject the maximum value from this table, that is 1, you only left with the value 0. And from here, so now you are left with the ML is equal to 0. And MS, the maximum values of MS are all the allowed values of MS is equal to plus minus 3 by 2 and plus minus half. So you write all the values of ms and you can choose the maximum value of that one. So the maximum value of that one is equal to plus 3 by 2. So we have ml is equal to 0 and ms is equal to 3 by 2. So when l is equal to 0, this is paired with ls is equal to 3 by 2. And then we have the resultant state 4s. 4 is obtained from the multiplicity which we use 2 into capital S plus 1 will give you the multiplicity 4, and this simple capital S corresponds to L is equal to 0. So we have 4S. And this 4S states will exist how many times? 2L plus 1 times 2S plus 1. So putting the value of L is equal to 0 and S is equal to half, 3 half, you get that value is equal to 4. So you see that 2D states can occur 10 times, 2P state can occur 6 times, 4S state can occur 4 times. So the sum of these states is 20. So these states can occur 20 times. Thus, through microstate table, 4S, 2P, 2D can exist for the ground state 2P3 of the nitrogen. Okay. So you see that these are the three are the same states that we have also found using the symmetry arguments. But now we have found them through the table, which we call it as the microstate table. So microstate table approach is more powerful. The other technique is also useful. So now let's talk about the parity of terms arising from the 2p3. This 2p3 can be written as, because these are three identical electrons, we can write 2p, 2p, and 2p. For these three electrons, we can write L1 is equal to 1, L2 is equal to 1, L3 is equal to 1. Parity is given by summation of all orbital angular quantum numbers Li. So if you add all these 1 plus 1 plus 1, you will get 3, which is odd. It means the parity is odd. So with these terms, you have the odd parity. And the odd parity is designated by the symbol O as a superscript. The terms of the ground state of nitrogen after parity indication can be written as, so 4s superscript S naught, 4s naught, 2p naught, and 2d naught. These are the states corresponding to the ground states of the atomic nitrogen with the indication of parity. That's the odd parity. This O stands for the odd parity. Now let's calculate the total value of quantum number J. For this state, the value of J is given by a mod of L plus minus S. So L is equal to, for the term simple S, the value of capital L is equal to 0, and for the multiplicity 4, the value of capital S is equal to 3 half. So the total value is equal to 3 half. So for this state, which is 4s not state, the value of the total quantum number J is equal to 3 half. Now let's talk about this 2p not state. The value of value of L is equal to, the value of capital L is equal to 1 for the P state, and the value of this 2 multiplicity 2 is equal to half. So adding 1 plus minus half will give you J is equal to 3 half and 1 half. So for the D state, you have capital L is equal to 2, and again the multiplicity capital S is equal to half for this state. So 2 plus minus half will give you capital J is equal to 5 half and 3 half. So now I can combine all these states, and I can also write down the total quantum number J with them. So the terms of the ground states of the nitrogen in full form: 2 principal quantum number, 4 multiplicity, S term symbol, not indicating that it is an odd state, odd parity state, and 3 half is the value of the total quantum number J of the atom. Similarly, I have written these quantum numbers over here. But you know that now I am going to distribute them in energy wise. If the value of the capital J is greater, then of course, but let's start with the basics. Now I want to arrange these terms in energy wise. That is, I shall write on the left hand side the term with the lowest energy, and I shall write on the right hand side the term with the highest energy. So for these terms, look at the multiplicity. The multiplicity is maximum for this term. The term with maximum multiplicity is the term with lowest energy. Now we have these two terms. They have the same multiplicities, 2 in each case. If the multiplicities are same, then look for the value of capital L. For the P state, capital value is equal to 1. For the D state, capital value is equal to 2. The term after the multiplicity, if the multiplicities are the same, look for the value of capital L. If capital L is smaller, then the terms is lower in, then the terms is, if the capital S is larger, for the case of, for example, D state, the term is lower in energy. So this D term lies lower in energy. Now the third term we are left, and of course that will have the maximum energy. So the lowest one is 4s energy, 4s term. The next one is a 2t term. The third term is the highest energy, which is the 2p term. Now I have also written their quantum numbers, total quantum numbers in the increasing order. So the term with quantum number 3 half is smaller in energy than the term with the d 5 half. Similarly, the term with p 1 half is smaller in energy than the term with 3 half. So you see that I have distributed them energy wise also. And these are the three states which I have written in full in energy wise distribution for the ground states of the nitrogen atom. And here you see that I have applied the first Hund's rule, which states that states with the highest multiplicity, which is given by 2s plus 1, is the lowest stable and thus lies is the most stable and thus lies lower in energy, lowest in energy. So the term with the highest multiplicity is the most stable term, lies lowest in energy. Now the Hund's second rule states with the same multiplicity, the term with the highest L is the lowest in energy. So if you have the two terms with the same multiplicity, then the term with the highest value of L will lie lower in energy. And of course, the rest one with the highest energy is the highest energy. Now for identical terms, that is P is identical with the two values of J. J is equal to half and J is equal to 3 half. Similarly, these are the two D terms with J value equal to 3 half and J value is equal to 5 half. So for identical terms, the lower J lies lower in energy. That's why I have written 3 by 2 on the left hand side and 5 by 2 on the right hand side. So you see that here in the today's lecture, what I have done, I have explained the LS coupling. I have explained which quantities are more stronger in interaction than other quantities. So Li and Lj combines to give you capital L, Si, Sj combines to give you capital S, and then capital N and capital S combine to give you total angular momentum J. So that's why it is called LS coupling. I have explained the LS coupling, their vectorial representation, the allowed selection rules, the spin quantities have also been explained, the total angular momentum J of the atom and the total angular momentum and total quantum number have also been explained. Their vectorial representation has also been given. Then the total form of the complete nomenclature for writing a term symbol has also been given. That is, the energy state can be written like this one. Then I have explained the name of the terms for the 2 electron, 3 electron, 4 electron, 5 electron. And then I have analyzed the ground state of the atomic hydrogen using the LS coupling initially. And then I have taken the support of the symmetry arguments to select which of the terms are allowed and which are not allowed, and then it has been supplemented with the technique which is called the microstable state technique, which is a more powerful technique, and then this technique also supplemented the LS coupling, and then of course we can select which of the states are possible and which of the states are not possible, and how many times those states could occur. And then I have arranged them. I have found the I have found the odd or even states, which states will be applicable. So I have found that then all the terms in the nitrogen are the odd state terms. And then I have arranged the energy wise. I have arranged all the ground state terms energy wise. And in that connection, I have used Hund's rule 1 and Hund's rule 2, and also the rule that governs the value of capital J in energy. So you see that these are the things that I have explained, and this lecture is continued. That is, many electron atom category of the lectures is continued. And in the next lecture, probably that would be the last lecture of this category, I shall cover the remaining part of that one, and I shall also explain the JJ coupling there. So this is the end of slide number 15B of the course on atomic and molecular physics, and the lecture is continued.